Now let's look at some examples of exercises that I want you to work with me today by following these videos. So the first exercise is consisting of trusses. All the members here are trusses. And the way I've set it up is that we will be able to fill in the blanks here now. So are there, if we want to make any other observations, then it's very simple for me. I can say that there are a certain number of trusses. So we have 3, 4, 5, 6, 7, and 8 trusses. So the trusses are of an even number. Even if they weren't, well, they wouldn't make really much of a difference to me. What I notice here in the figure is that there are certain sections which are repeating. So if I look at this section right here, it's repeating each time when I move from one section to the other. But what I also notice is that there are two boundary conditions that are applied, and these boundary conditions are only applied at the two opposite nodes from each other. So that means I have boundary conditions which sort of looks reflective about a certain axis that is right over here. And what I also notice is that the geometry is also symmetric about this axis. And the geometry is also symmetric about this axis. So let me use blue one for geometry being symmetric. But about the blue axis, the loads are not symmetric. If the loads had to be symmetric, then I had to have some conditions on the other side as well, which is not true. Although the geometry is symmetric, we cannot use the blue axis for symmetry. So the only one we are left with is yellow. Now what we notice is that there's a load which is acting, and this load is acting at the axis of symmetry, and there's no other load acting on the entire assembly of these trusses. So it is safe to assume that this is the line of symmetry for the entire structure. So once we've identified the line of symmetry, we can start reducing the structure that we are looking at now. So I'm going to just start drawing from the left hand side. So I know that there is a certain node here which was numbered as node 1. Then I go to node 2 to 5, 1 and 5 are connected. Then I go to number 4, and also 4 and 5 are connected. So I'm going to just number them 1, 2, 5 and 4. So the only node that actually drops out is number 3. I know that there is a boundary condition here which is fixed, so I'm going to maintain that. So this is basically the reduced geometry and the reduced boundary condition. Now, as I already mentioned before, there always have to be some improvement or some adjustments that have to be made to the model once we have reduced it using symmetry. And the first one would be to update the boundary conditions. Now we know that at the symmetry plane, there are some things that the nodes would not be allowed to do if it was a full fixture, as it is shown of the full assembly. So one of the things that I want to do before that is form the coordinate system. So I'm just going to write a coordinate system over here, although it's not very relevant, but it's always useful to work with coordinate systems. So here we know that it would, if I have a node here and these two members are joined here, it would not be allowed, or there would be certain resistance for it to move in these directions, just as it is, without application of any load which would be acting in that direction. So it's safe to say that it should not be allowed to move in this direction at both, at both the nodes. So this one and number 4. So it's not allowed to move in this direction, so we fix it in this direction only. But we know that there is a load P that is acting on the structure, and because of this load P, it's possible that this truss the point will always move downwards. That's always possible, both these points 2 and 4 and 5. So therefore it must be allowed to move in the, also at 5 it should not move in this direction. So that means we are allowed to move in the Y direction. So we are allowing it to move here, but we are not allowing it to move in this direction. So that means we will have roller supports which are going to fix the displacement such that this line can move up and down in Y, but it cannot move horizontally. So this is now our updated boundary conditions. So it looks okay. Now the only thing that is left for the adaptations, as I mentioned before, is the load. Now for the load, I know that the load P is supposed to be applied to the entire structure. So if I reduce the size of the structure and the load is applied at a point, that means it's a concentrated load, then I must always halve the load or divide the load depending on how many divisions I've made to the geometry. So now in this case, my geometry is halved, so I need to apply half of the load. Now this problem is slightly more challenging than it looks like for boundary conditions and loads only, because we also have to realize that I said the geometry has been halved. And if you notice carefully, then there are these two elements here and here, these trusses, which are intact. However, we cannot do that. We cannot use them as intact if we want to halve the geometry. So it's also required that we reduce the area of these members by half if we want to use them in the symmetry conditions, which of course we have to because it's part of the structure. So there are three things that we learned from here. The three things were, first, that the boundary conditions had to be updated in such a way that in the symmetry plane, you will have only rotations that will be fixed. In this case, we do not have any rotation, so that didn't matter. But perpendicular to the symmetry plane, we have to fix it. That means it was not allowed to move in the x direction, while the symmetry plane is the plane, is the y. So the yz plane here, which is the z is out of plane, is the symmetry plane. And the axis of symmetry is the y-axis. So we had to fix perpendicular to that, and we allowed it to move in the plane of symmetry. When we had to use the loads, then since the load was concentrated, I had to divide it. And then finally, if I have geometry that is present at symmetry, plane or symmetric axis, I also need to divide the area accordingly. Okay, so this is one of the more complicated problems. Go through it again, work it out yourself once, and see if you understand it carefully and you see if it is correct. If there's something that's wrong, please don't hesitate to let me know.